Okay, so in this lecture, I'm going to present the material in chapter 2 of the Bayesian textbook. I'm going to start sharing my screen so you can see my slides. Right, so here are the lecture. Here's the slides for the lecture, and we're going to start by talking about Bayes rule, which I believe I introduced in um, chapter 1 already, when I talked about conditional probability. But just to remind you, the basic idea is that if you're talking about two discrete events, A and B, we can ask questions like, what's the probability of A happening given that B has already happened? So that's the conditional probability rule that we've already seen in equation 1. And the interesting thing about this rule is that it allows us to derive Bayes' rule, right? So Bayes' rule is simply a consequence of the conditional probability rule. Now, how this works is that we know that the conditional probability of A given B is equal to the joint probability of A and B divided by the probability of B, provided the probability of B is greater than 0, because division by 0 in um, in normal situations is not defined, right, in mathematics. So, so if we rearrange, equation 1 such that we have the joint probability term on the left-hand side, then what we end up with is the statement that the joint probability of A and B is equal to the conditional probability of A given B multiplied by the probability of B. Now, one cool fact is that the probability of A and B, the joint probability of A and B, is the same thing as the joint probability of B and A. So the order in which you write the two events is irrelevant, right? And so because of that, we can now equate the probability of A and B to the probability of B and A happening. They're of course the same thing, obviously, right? So, but the interesting consequence of that is that the probability of B and A happening, so the order in which we write these two guys actually affects how the right-hand side, this equation plays out. So instead of writing probability of A and B, we're writing probability of B and A, and that changes the B and A terms. If you compare this statement with this statement here, you see that the A's and B's are flipped, right? But the interesting thing is that this statement is the same as this statement here, right? And what's interesting about that is that this leaves us with these two sides of this equation being exactly the same thing, representing the same thing. And so what that gives us is equation 3, because now if we divide this term by the probability of A happening and divide the right-hand side also with the probability of A happening, we end up with Bayes' rule, which is equation 3, right? Which says that the probability of B given A is going to be equal to the probability of A given B times the probability of B divided by the probability of A. So this Bayes rule is what we're going to be using in this course for doing statistical inference. This equation that I'm showing you here is specifically with reference to discrete events. So I was talking about discrete events A and B, but we can use the same equation to talk about probability distributions, right? So what we're talking about here in equation 4, we are looking at Bayes' rule here. It's exactly Bayes' rule, but instead of talking about the probabilities of discrete events, right, we are talking about probability distributions here. So that's why I've switched from using P, capital P, it stands for probability, and I've started using F, which stands for probability density function. So what's going to happen now is that we are going to use the right-hand side of this equation to work out the left-hand side to find a way to represent the left-hand side, right? So I will unpack this equation now in the context of statistical data analysis. But before I do that, I need to explain what this denominator here is. So the denominator is f of y. So what these terms actually are referring to, theta is the parameter of interest that we are trying to find out something about given the data. Y is the data. And what we are doing here is that the Bayes rule is what it's actually saying is that the distribution of the parameter of interest theta given the observed data that we have is going to be equal to the likelihood of the data, that's f of y given theta, multiplied by a prior distribution on theta and divided by the what's called the evidence. Okay, so divided by f of y. And now the question is, what is f of y? So I'm going to explain that now. F of y is actually what it's doing is it's taking the joint distribution of y and of theta. So y is the observed data, theta is the parameter of interest, and it has some probability distribution associated with it. Now, we take the joint distribution of y and theta, and we are integrating out the theta parameter, right? That's what this right-hand term is doing. And what it does is, once you integrate out a parameter, you're going to end up with the f of y here, right? So this issue about this mathematical operation, integrating out a parameter, is discussed in chapter 1 as well, but I'm going to give you a simplified example of what it means to integrate out a parameter, okay? But what's important to understand is that the end product of Bayes' rule is going to be a distribution that represents the distribution of this parameter of interest theta given the data that we have seen so far. So that means the left-hand side term is an actual probability density function, right? It's a proper probability density function. And what that means is that like every probability density function, it has a kernel and it has a normalizing constant. Because the normalizing constant, the sole purpose of that normalizing constant is to ensure that the area under the curve in this probability density function sums to 1. Okay? So that's why I write here that f of y is the normalizing constant. So this, in this equation, the numerator is actually the kernel of the distribution, and the denominator here is the normalizing constant, which ensures that f of theta given y, the distribution of theta given y, is a proper probability density function. That means the area under the curve sums to 1. Okay? So let's take a look at what it means to integrate out a parameter. Okay? So imagine, let's simplify this problem. So here we're talking about integral calculus, but we can simplify this problem by discretizing it, okay? So then we can get a better handle on what it means to integrate out a parameter. So this term that I've written out here is basically just a continuous version of this statement in equation 6, because what I'm saying here in equation 6 is that suppose, that we have a suppose that we have a discrete distribution defined over the different possible values of theta. So let me illustrate what that means, okay? So I could come up with uh, a distribution that represents, for my theta parameter, the theta parameter could have three possible discrete values. Could have three possible discrete values that are equally likely. Okay, so this is a discrete. This would be a discrete prior distribution on theta, right? The reason it's called a prior distribution is that this is a distribution that we are defining prior to actually seeing any data, right? Or prior to seeing the actual data that we are about to collect, right? We might have seen other data that gives us reason to believe that this is a reasonable prior distribution. So we've defined a prior on this prior distribution on theta, and because this is a discrete distribution, so I could say something like 0.1 here, 0.5 and 0.9 are possible values of theta, assuming that theta is, probability or something like that in a binomial distribution. So if all these three are equally likely, if all these values are equally likely, so then this value on the y-axis has to be 1/3 because these probabilities of these three possible values of theta have to sum to 1. Okay. All right. So that's an example of a discrete prior on theta. And so I'm going to talk about how we can get the f of y in this situation where there are discrete values for theta that are possible, and each of those discrete values has a particular probability, like I just showed you in the figure, right? Now, what are we going to do? We're going to take the likelihood function, whichever likelihood function we are interested in, for example, the binomial, and multiply the likelihood function with that one particular value of theta plugged in, and then multiplying that particular value, that likelihood function, with the probability of that particular value. Okay, so I will explain this next. So suppose, let's make this really concrete. So suppose that we're talking about a binomial distribution. There are 10 trials and 7 successes, right? So in this situation, the probability mass function is the one that we are familiar with from the binomial distribution. And here, this is my likelihood function now, right? This is the likelihood function because the only variable here is theta. The data are now known, and so they are fixed numbers here, okay? So as I said earlier, if you have a discrete set of possible values for theta, call them theta 1 is equal to 0.1, theta 2 is 0.5, and theta 3 is 0.9. We are now going to marginalize out all the possible values of theta in the following way, right? First of all, we know that the probability of each of those theta values is 1/3. That's that figure that I just showed you, right? This figure, right? So we know that, right? That what the probabilities of each of those possible three values are. And so what we're going to do is we're going to take the likelihood function. We're going to take the first value of theta and plug it into the likelihood function and multiply that with the probability of that particular value of theta, and do that for all the three values and sum up the result, right? So what we are basically doing is we are computing something called the marginal likelihood, right? And this is exactly the same thing as integrating out the parameter. So what we're doing is we're computing a weighted sum of the likelihood weighted by the probability of each of the possible values. Now, this is the discrete case. So it's easy to work this out as a summation, right? So let me just do the math. So if I do this calculation, I'm going to end up with some, you know, uh, numerical value, a constant. This is going to be a constant, and this constant is that f of y that I was talking about earlier, right? So it's this f of y that I figured out. And the reason I'm talking about this is because I'm showing you how this f of y in the denominator can be computed by integrating out the parameter or parameters in the likelihood function. All right, so that's a good example of how that's an easy to understand example of how you marginalize out, how you compute the marginal likelihood and how by integrating out a parameter. Okay, so we can do this entire operation. Sorry, where is it? Yeah, so we can do this entire operation in one shot in R by using the d binom function. Here is the observed number of successes, number of trials, the three probabilities, the three possible values of probabilities that I mentioned. And what I'm doing is I'm taking the likelihood with each of these possible values, multiplying it with 1/3, and then summing up the result. And I get exactly the same number that I get over here by doing this calculation. So you can see the convenience, of using this DPQR family of functions. They help you, quickly get a handle on many of these ideas. So now we know what computing the marginal likelihood involves. It involves integrating out a parameter. And so this is basically what we are doing, when we are, go back here. If I go back to this equation, right? So we're just integrating out the parameter here, right? The only difference will be that in continuous space, we're going to be doing this with integral calculus. It's just a summation, but in continuous space. All right, so so what's interesting here is to notice that if we just ignore the normalizing constant, we can talk about the posterior distribution of theta given y up to proportionality. And we can say that the posterior distribution of theta given y is proportional to the likelihood times prior. So that's equation 12, right? So this is often, abbreviated as shown in equation 13. The posterior is proportional to the likelihood times the prior. Okay. Well, one reason why we might want to just focus on the Bayes rule up to proportionality is because the normalizing constant is something, well, first of all, it's a constant, right? And secondly, we can actually work that constant out pretty easily once we know the posterior distribution. And so that's something I discussed in chapter 1, but I'll quickly do a short excursus on this, just to give you an idea of what I'm talking about. So when I say that we can always work out the normalizing constant, imagine that you have some probability density function, right? F of x, right? And um, let's say if it's f of theta or something, right? So there's some probability density function, but the normalizing constant is missing, okay? Now, we know that the purpose of the normalizing constant is to ensure that the area under the curve in this distribution and in this probability density function, the area under the curve has to sum to 1. So what does that mean mathematically? It means that the integral f of theta d theta, right? There has to be some constant k such that this equation equals 1, right? K times the integral f of theta d theta is going to have to be 1, right? So all you have to do is solve for k, right? Solve for k, and in easy cases at least, this is going to be easy to do because all we have to do is 1 times 1 over f of theta d theta. This gives me the normalizing constant. So this normalizing constant, once I know, in the context of Bayes rule, f of theta given y, if I know this probability density function, f of theta given y, up to proportionality, that means I know the product of these two. And of course, I will show you how all this works in a moment. Okay. Once I know this probability density function, if I want to make it into a proper probability density function, namely making sure that the area under the curve sums to 1, the normalizing constant I can work out. Once I know the form of this probability density function. Okay. This is discussed in chapter 1, by the way. Okay, so just go back and look at it in case you haven't seen it. All right, so the next thing we are going to do is we are going to use Bayes' rule in a simple analytical way so that we can actually derive a posterior distribution given some likelihood and given some prior on the parameter of interest. So I'm going to work with this simplest, example that we have already encountered earlier, the binomial distribution. We're going to use that likelihood function. And I'm going to have to define a prior on the theta parameter, which represents the probability in the binomial. And then we're going to proceed from there. I'm going to literally multiply the likelihood with the prior to get a posterior, right? All right, so let's go. Let's talk about this discrete case of the binomial likelihood. So this is just what I've just been talking about, that what our goal is going to be to figure out the posterior distribution of theta given the observed data. And we're going to do that by applying equation 15, which tells us up to proportionality, what the um, posterior is, posterior for theta is, okay? So we, of course, know, if you look at equation 15, we know what to write here. This is going to be the binomial distribution, right? So, for example, if we have 46 successes out of 100 trials, then the likelihood function up to proportionality is this term here, right? So I can replace f of x given n theta in equation 15 with the kernel of the binomial distribution for the particular case where I have 46 successes out of 100 trials. The only thing that I don't know how to proceed with is how to define a prior on theta. So that's the next thing we're going to think about, right? So we're going to have to decide on some distribution for theta that we can incorporate into our model so that we can carry out the computations for Bayes rule. So this prior distribution on theta, the goal here is to represent our uncertainty, our prior uncertainty about plausible values of theta, right? So if you think about it, there's several intuitively, what could be plausible values of theta in the binomial distribution? Well, we know that the range of theta has to be between 0 and 1. So what we want to do is describe some probability density function that represents our uncertainty about theta, prior uncertainty about theta before we've seen this particular data of 46 successes, 100 trials. So we are deriving the prior distribution for theta before actually seeing the data. Right? That's what we're doing. So one possible, prior distribution that I could come up with could be a uniform distribution, right? So what this distribution would say is that a priori, every possible value of theta is equally likely. That's one possibility. Another possible prior distribution I could come up with would be something like this, right? It could say that I think that the average of the prior distribution of theta is about 0.5, but I'm very unsure about what the exact value is. So it could be very close to 0, it could be very close to 1, but it's less likely to be close to 0 and 1 and it's more likely to be, in this high density range, right? That's one way to, another possible prior that I could define. Yet another prior I could define could be something like this, I could have very tight certainty that theta is very close to 0.5, right? So these are different priors. And of course, there are infinitely many possible priors that you could come up with. I'm just showing you three, plausible examples depending on what you think are plausible values for theta, right? So such a tight prior, this is a very, very tight prior. This kind of prior would actually make sense if you're defining a prior distribution on, for example, a coin that you know is fair, right? There is pretty likely that you're going to get a 50% probability of heads a priori, even before you toss the coin. A wide prior like this, but still at 50% accuracy, average value could represent, a situation where you're asking individuals with aphasia yes no questions about non-canonical word order sentences. So we know from previous research that people with aphasia, they are roughly at 50% accuracy for answering such questions, but there's a lot of variability in their behavior. So you wouldn't want to type prior on theta in that situation. A uniform prior like the one I'm showing here, this could also be reasonable in some situations where you know absolutely nothing about your problem. So you're starting with absolutely zero knowledge and anything is possible. You could have 0% accuracy or 1% or anything in between with equal likelihood. So these are all possible priors that one could set up. But the question now is, how do we set up such a prior? Well, it turns out that there's actually a distribution in statistics called the beta distribution, which takes two parameters, A and B, and the beta distribution actually creates a shape that has the properties that we want it to have. It ranges, the support of the beta distribution is between 0 and 1. And these parameters A and B in the beta distribution are going to ensure that the shape of the beta distribution is what we want it to be. Okay. So the way we interpret the A and B parameters is you can think of the A parameter as the prior, expected number of successes that you're expecting, and B as the number of failures that you're expecting, right? So for example, if you set up A equal to 1 and B equal to 1 as your values for this beta distribution, right? This A equal to 1 and B equal to 1 means that you are actually defining a uniform distribution over the parameter space, right, over theta, right? That's what it will come up to, right? If I if I were to increase these numbers here, so let's say I make them A equal to 10 and B equal to 10, then what will happen is that the curve will start changing shape and it start looking like this, right? Now, what does the actual beta distribution look like? This is what the beta distribution looks like, right? So this beta distribution is the kernel of the distribution is these terms over here. And notice here it says that the support of theta of this parameter theta is going to be between 0 and 1, right? And so the kernel of the distribution is this part here, and the normalizing constant is, as I explained earlier, it's the integral of the kernel, right? As I showed you earlier. So, but the kernel is really the interesting part. This is, sorry, I uh, tried to make highlight just this part, but the kernel is the really interesting part here, right? Because we're trying to compute the posterior up to proportionality. Okay. All right, so here's the beta distribution. The A and B, values that I just talked about, they would go in here to determine the shape of the curve. And I'm just going to show you the curves in a moment. What happens when you put in different values for A and B in this probability density function. Okay. Now, just as an aside, in R, we have the DPQR family of functions for beta, the beta distribution as well. So for example, we will have d beta that allows us to draw the probability density function to plot it. And there, instead of writing A and B, in R, they use shape 1 and shape 2 for reasons unknown. Okay, so it's just a different term that they use for A and B. So whenever you see shape 1, that represents the parameter A, and shape 2 represents the parameter B here, okay, for the prior distribution on theta. And given A and B, once we know what A and B is, or once we've decided on that, we can figure out the expectation um, the of the beta distribution and the variance of the beta distribution, right? So these are the equations for the expectation and variance. And this makes sense, right? Because like I said earlier, A represents the number of successes, B the number of failures. So the expectation is the proportion of successes, right? So that makes sense. So, so as I said, the beta distributions parameters A and B are going to be interpreted as our beliefs, are going to represent, our beliefs about um, the theta parameter, right? So once we decide on the values A and B, we can plot the beta probability density function. It's very easy to do, and I'm going to show you now. The code, of course, I will provide later on, so you can play with it yourself, okay? But basically what I'm doing here is I'm setting different values for A and B. This is A equal to 1, B equal to 1, uniform distribution. A equal to 3, B equal to 3 gives you a widely spread out distribution centered on zero 0.5. A equal to 6, B equal to 6 gives you a slightly tighter distribution. If I had done A equal to 60 and B equal to 60, I would get a super tight distribution centered on zero 0.5, right? And of course, you can move the peak of the distribution left and right by changing the A and B parameters, right? So if you had A equal to 6 and B equal to 60, you're going to end up with a beta distribution leaning towards the left. Let me do that, okay? Let me just show you how that works. So let me just create like a vector of theta values, right? 0 to 1 by 0.01, right? And then I'm going to just plot the theta values on the x-axis. And using the d beta function, I'm going to plot the density of the theta values for shape 1 equal to 6, for example, and shape 2 equal to 6, right? Also 6. So this will give me and I'll draw a line here. Let's see, right? This will give me a symmetric, plot centered on 0.5. The peak of this curve is at 0.5 on the x-axis. But if I change the shape 2 to 60, that'll shift the curve to the left. Right? That's the beta density. So the way we are going to use this is that we're going to use, these are prior distributions that we can define on the theta parameter. And we have uh, as modelers, we have to make a decision about what a reasonable prior would be for this particular theta distribution, theta parameter. And I'll talk a lot more about deciding on the prior later on. But right now, I just want to say that if you use A and B equal to 1, create a uniform prior on theta, then we would say that that's a relatively uninformative prior in the sense that it allows all possible values between 0 and 1. If we happen to know something about our problem, like I was talking about a fair coin, you already have very strong beliefs that if you're going to toss a fair coin, most likely the probability of heads is going to be close to 50%, right? So there I might set a tighter prior for theta, right? And so there's going to be a gradation in the degree of certainty that you will put into the prior distribution depending on your prior knowledge about the problem and your starting point in your research question. I'll come back to all that later on, okay? But right now, I just want you to understand that we have a range of choices. And so what we can do is just for the sake of argument, just to understand the machinery of Bayes' rule, we're going to plug in different priors to see what posterior we get every time we plug in a prior. Yeah. So this kind of analysis is something that we do a lot in Bayesian data analysis. This is called a sensitivity analysis. You're trying to find out if the posterior distribution of theta given the data is sensitive to the specification of the prior. This can be an important thing to check, as I will discuss later when we get into the nitty-gritty details of Bayesian modeling. All right. So what's common, to all these four priors that I've defined here is that the expectation here is going to be 0.5, right? We are expecting 50% accuracy a priori, or 50% or 0.5 as the most likely value of the theta parameter a priori, okay? So, but what's different about these four distributions is the degree of uncertainty that we have about that value 0.5 as the a priori value. Sorry, I'm about to sneeze. Right. Okay. So here we go. Okay, so equation 17 is the Bayes rule right up to so up to proportionality. And so what we're going to do is we're going to take the likelihood, the kernel of the likelihood. We're going to multiply it with the kernel of the beta distribution. Okay, so let's just let me just do this on the iPad for a second. If you remember, what's the kernel of the beta distribution? And let's go back. The kernel of the beta distribution is theta a minus 1 times 1 minus theta b minus 1, right? And what is the likelihood function? Right, so let me just write this out. So what's the likelihood function? The likelihood function, this is the prior, the kernel of the prior. The likelihood function is, the kernel of the likelihood function is theta to the power of number of successes, right? Multiplied with 1 minus theta to the power of n minus k. N is the number of trials, right? So what we are doing is this product is going to give us the kernel of the posterior distribution. The kernel of the posterior distribution is easy to work out given this term that these terms that I'm showing you on the iPad. And so I'm just going to rearrange these terms now. I'm going to put the thetas together. Theta k times theta a minus 1 times 1 minus theta n minus k times 1 minus theta, right, b minus 1, right? Now, once I can simplify this and I can simplify this, right? Because this becomes theta to the power of k plus a minus 1. And the next term becomes 1 minus theta n minus k plus p minus 1, right? And so if we just look at this result here, this result is again the kernel of a beta distribution, right? Let's go back. Here's my beta distribution. This is just the kernel of the beta distribution again, because it has the same form. Instead of a minus 1, it is k plus a minus 1, k plus a minus 1, right, over here. This is my new a. And instead of b minus 1, what I have is n minus k plus b minus 1. This is my new b. So what's happening is that once I've seen the data, and in this case, the data is k and n, that's our data. The posterior distribution of theta ends up also being a beta distribution if we define a beta prior on theta. And the updated a and b parameters of the beta distribution for the posterior become the following. I'll call them A star to distinguish it from A. A star is going to be K plus A, and B star, the new B parameter after we've seen the data is N minus K plus B, okay? So what's going on here? Intuitively, it should be clear that what's going on here is that having seen the data, we are updating the A and B parameters to represent our updated belief about the theta parameter. And that belief will be represented as a posterior distribution, right? So What I've just done is I've just taken the kernels of the likelihood and of the prior, that's this line here, solved, simplified the equation, and I ended up with a beta distribution that represents the posterior of the theta parameter up to proportionality. I'm ignoring the normalizing constant because it's going to be easy to work it out, right? It's going to be super easy to work it out. And I don't really need to do that. So in this particular case, at least, right? So what happened here now is what I've just done is that I've just calculated the posterior distribution of theta given x under different priors, right? So in this first line here in equation 18, I'm using a and b equal to 1. A and B equal to 1. In second one, this is my second prior that I've tried out again. I've got A and B equal to 3. Then I've got A and B equal to 6. And then A and B equal to 21 and 21, right? And so what you're looking at here on the right-hand side of these equations, in equations 18 through 21, is the kernel of the beta distribution that represents the posterior distribution of theta given the data that we have observed. Okay. So we can observe each of these, triplets of priors. Um, so this code, you can look at this code later on, but basically I'll show you the results first. Okay. So what I'm doing is I'm showing you the for one particular prior, right? And for the observed data, which is represented by the likelihood, right? The likelihood is this broken line here with these long lines. It should be centered on 46, right? Because I had 46 successes out of 100 in my data. That's what I'm assuming. I'm showing you the prior distribution for A equal to 21, B equal to 21. That's this prior here, right? This prior centered on point 5, yeah. And the solid line is representing the posterior distribution of theta, having seen the data. And so one important thing to notice in this figure is that the posterior distribution of theta, that is the solid line, lies somewhere between the scale likelihood function. So I scaled the likelihood so that it it has the same, it fits into this plot. Okay, I just had to scale the likelihood because likelihoods, they're not proper probability density functions. They don't, the area under the curve doesn't sum up to one. But I wanted to draw three proper probability density functions. So what I did was I scaled the likelihood such that it becomes a probability density function so that I can plot it alongside the prior and the likelihood. Okay? So that's why it's called a scale likelihood. So what you should notice is what I was trying to say just now before I got sidetracked was that the posterior distribution of theta, the solid line, lies between the scaled likelihood and the prior distribution. So it's a compromise between the prior and the likelihood. And this will generally be the case that your posterior distribution has the property that it will be a compromise between the prior and the likelihood. Of course, there's a wrinkle here that I will explain later on, but this is an important idea to understand that the prior distribution is going to have an impact in determining the posterior to the extent that the prior distribution is informative. If the prior distribution is completely uninformative, then the posterior distribution of theta is going to look pretty much like the likelihood. Okay. So the less informative the prior, the closer the posterior will be to the likelihood. And the more informative the prior, the closer the posterior will be to the prior. Yeah. So this is the interplay between the likelihood and the prior in determining the posterior, and we will get a better handle on this when we actually work with lots and lots of examples. Okay. All right, so this is a great starting point, because what I just showed you is a situation where we have a binomial likelihood and a beta prior. This kind of situation is called a conjugate case, right? So it's conjugate because by definition, a conjugate case is the situation where the posterior distribution has the same form as the prior distribution, right? So when you have a binomial likelihood and a beta prior, you multiply them together, you get a posterior distribution that's of the same family as the actually the same type of distribution as the prior, right? So that's what's called a conjugate case, and there are many such cases out there. This is not the only one. You have the Poisson gamma, Poisson likelihood, gamma prior, okay, on the parameter, or you could have a normal likelihood and a normal prior on the parameter, the mu parameter, let's say, right? So you'll get a posterior on mu that will be normal. So, um, and there's a bunch of others. I'll give you a list later on, or you can find them quite easily. So this is a classic example, of how you use Bayes' rule analytically without any computing involved to figure out the posterior distribution of um, the parameter of interest. Okay, so one interesting thing is that we have a general result here. If you take a look at this derivation that I just did, this is a very general result. So now we know that in the beta binomial case, now we know that as soon as we know what the number of successes k is and what the sample size is, right? We can, and of course, as soon as we know what the prior is on theta, right? If on theta we define some beta prior, right? This is the starting point. We define a prior on the theta parameter. We get some data. This is our data, right? We know from the analytical result that I just derived that the posterior distribution will be a beta distribution with parameters k plus a. So k plus, what happened here? K plus a. And for the b parameter, it's going to be n minus k plus b, right? So as soon as I know k and n, I just plug it in, plug in these numbers, and we know what a and b is because we decided on those ourselves, and we can derive the posterior. So no computing required. You can literally do this by hand. So it's a very useful and instructive example that gives us a good understanding of what happens when we multiply a likelihood with a prior to get a posterior distribution. So in the next example, I'm going to discuss another conjugate analysis, and this time this will be the Poisson gamma. I will do that in the second lecture, in the second part of this lecture, so as to not make this recording too long. So I'm going to stop here.